Moving on towards the last part of our week, which is Norton's theorem. The Norton's theorem basically is pretty much similar to Thevenin's theorem, with the only difference that it focuses on simplifying a circuit with respect to current sources. Thevenin's theorem again focuses on simplifying a complex circuit, and it after the result after simplification the result is in the form of a voltage source and a series resistance, right? Whereas when we are talking about Norton's theorem, it is similar to Thevenin's theorem in the sense that again it focuses on simplifying two terminal circuits. Its application is also the same, that complex linear circuits where only the load end is changing, they can be simplified, but the result or the output is different. Why? Because the result of Norton's theorem is in the form of a current source having a magnitude In and a resistance Rn connected in parallel. Rn and R Thevenin, that is Norton resistance, Thevenin resistance are basically the same resistance, right? So what Norton's theorem tells us is that it states that any complex linear two-terminal circuit can be represented as a simplified network with a current source of magnitude In connected in parallel with a resistance of value Rn. And here In is the short circuit current. In is the short circuit current through the load terminals. It will be S through the load terminals. And Rn is the resistance of the network as seen from the load terminals when all the independent sources are turned off. So basically R Norton and R Thevenin, that is Thevenin resistance and Norton resistances, they both are same. The circuit solution is also the same. The only difference is that previously we used to open load terminals, right? In this scenario, we have to short the load terminals and calculate the current through the shorted path, right? And then the simplified circuit will be in this form, that we will have a current source of magnitude In. And what is In? In basically the short circuit current across the load terminal. There is a parallel resistance which is Rn, which is basically the same as R Thevenin, right? And then in parallel again we have the load resistance which is RL, or which is the changing resistance, we can say, right? This is the changing resistance RL. Now one thing that we must see, that can we convert a Thevenin equivalent circuit into its Norton equivalent, or a Norton equivalent circuit into its Thevenin equivalent? Is it possible? Uh, just think about it. Just think about it. Is it possible to convert a Norton equivalent circuit by any means, by any theorem that you people have previously studied, into its Norton equivalent? Can we do this? Just think of it. We studied one theorem in the very previous lecture, that if a current source, here is a current source, has a resistance connected in parallel, right? Then we can convert that current source into a voltage source, right? With the same value of resistance in parallel. This is plus minus. We have the same value of resistance in series, sorry. And then we have the load resistance. So if we perform source transformation, then this will be R Norton or R Thevenin. We have already discussed that both of these are same. And this resistance is again the variable resistance, which is RL, right? So basically Norton and Thevenin equivalent circuit are nothing but the source converted format of one another. If I have, let's say, a Thevenin uh, equivalent circuit, I just need to apply source conversion to it, convert the voltage source into its equivalent current source, and I will get the Norton equivalent circuit. On other hand, if I have this Norton equivalent circuit and I need to find out the Thevenin equivalent one, I just need to convert this current source into its equivalent voltage source, right? So if I am given a circuit and I am asked to find both the Norton and Thevenin equivalent, then we just need to find one and apply source transformation. There is no point in doing very long analysis for all the for both the theorems, right? You simply need to do what? You simply need to calculate one equivalent circuit, apply source transformation, and find the other, right? So this ends our week number 7, and we have gone through a lot of theorems here. And there is one theorem which is left, that is the maximum power transfer theorem, and which states that the power transferred across a circuit is maximum when the load resistance is equal to the Thevenin resistance, and there is a derivation related to that problem, and I will be posting that derivation on the group. And uh, otherwise we are done with circuit theorems. So I hope that you people are now able to understand superposition, source transformation, Thevenin's theorem, and Norton's theorem. So in the next week we will start the new topic, and till then it's goodbye.